Good morning, everyone. My name is Stewart, and I'm coming to you from Toronto, Canada. And I'm very pleased and very honored to be invited to contribute to this workshop, even though from a great distance. But it's very I'm very happy that I'm able to join this and to maybe offer some help and some overview of the system itself, and that might help to guide some of the projects that are underway. And many of these are excellent projects in Chinese cities. So this is quite a pleasure for me to be involved. I'm going to go through some basic principles of the local climate zone system that I think are important, that everybody should be aware of and should understand before getting too involved in the local climate zone scheme itself. I'll also reflect a little bit on some practices that I think are good practices and are recommended practices, and help to address some of the confusion that's been expressed in certain aspects of the LCZ system. And then we'll take a few minutes to look at some international examples of LCZ usage in different cities around the world. And in my opinion, these are some good examples, very illustrative of the variety of applications that LCZs can be used for, and the variety of users and background disciplines that can make good use of the system itself. So we'll go through this. It'll take about 20 or 25 minutes, and my hope is that it's helpful in some way to all of you in your studies of climates of cities and architecture and form and function of cities, and in particular to the students who are learning the system itself and using it to collect data and to understand how the morphology of cities is very closely related to the local climate of cities. So with that, I'd like to start off with what I call the root of the problem, and this is really about the need for the LCZ system in the very beginning. And this goes back more than 10 years ago to a conversation that I had with Professor Tim Oak at the University of British Columbia in Vancouver. And at that time, he expressed a very deep concern of his that much of the literature that's being produced in urban climatology is lacking in metadata, in site metadata. In other words, we know very little about the physical characteristics of the sites where we place our instruments and our sensors to gather climate data. And this is what we call site metadata. So this was the beginning of the LCZ scheme, and it was the beginning of a doctoral project for me. And my first task was to do a literature review of the heat island and the urban climate studies worldwide, and to come up with some indication of how much metadata, how much physical description of urban climate sites was being provided. So to summarize that, we can say that in urban climate literature, field sites are too often classified according to their location. In other words, we only know if they're urban or they're rural, or we know something about the land use, or we know some other qualitative description about the sites. What's missing there is some quantitative measure of the sites. In other words, how tall are the buildings? What is the spacing of the buildings? What is the surface cover? What is the traffic flow? What are the sources and sinks of heat around our sites? And you can see here by this pie chart that in a study of about 190 published peer-reviewed papers, 30% of them told us nothing whatsoever about the sites. Another 30% told us, or 40% told us something qualitative. So this is quite concerning for the literature, and it led directly to the need for some kind of classification system to fill that gap. And this is a good illustration of that gap. Here I've put 4 photographs of sites that are all classified as urban in the climate literature. However, none of these studies provide any information about what those sites look like. And so part of my work to develop the scheme was to travel to these cities and to these sites and to collect some, or to document some photographs about these sites. And you can see here they're very different. On the top left we have a modern street with glass high-rise buildings and a very narrow canyon. The radiation balance inside this canyon is very different from the other pictures. The exposure to the sky, the airflow, the heat sources, and so on. And the other cities here, or the other streets here, have their own unique physical characteristics and own unique street morphologies and so on. And so without the physical metadata attached to these sites, we're simply guessing at what the temperature measurements represent in terms of the urban form and the surrounding area of influence. Some people suggest that using a land use classification is an improvement. I don't think it offers much an improvement, and that's illustrated here. On the bottom half of this photo is a residential area in Toronto where I live. This is the street on which I live. And on the top half is a residential area in the city of Jinan, China. And it's probably representative of how many people in China live in high-rise apartment buildings. And many people in Canada here live in the low-rise dwellings. But you can see that there are obvious differences between the two. So classifying our sites into land use is not fully satisfactory. So the solution to that is to characterize the surface elements and the surface facets of the urban environment into categories that are relevant to local climate, and categories or characteristics that can be easily quantified and easily measured. And in doing that, we came up with 4 relevant surface properties into which we can place the building and surface characteristics. So the first one is the height of the roughness element. So these are the buildings and the trees. And taking cities internationally, we can easily classify these into 4 different categories: high-rise, mid-rise, low-rise, and no-rise, and easily assign a range of height values to each of those categories. And we can do the same with vegetation: trees, bush, grasses, and soil. So immediately we have the beginnings here of a breakdown of the urban and the rural environments into something that's more meaningful for a climate study. We can carry that through and look at the packing of the roughness elements. How closely spaced are the buildings? Are they compact with a height to width ratio of greater than 1? Or do we pull them apart and they start to open up? And even further still, we find ourselves with a sparse arrangement. This is all determined by the height to width ratio of the buildings or the canyons. And again, to make this system applicable to natural environments, we have to consider the vegetation and the spacing of the trees. So that's the second criterion. The third one is the surface cover around the roughness elements, around the trees and the buildings. And this is 3 simple categories: impervious, meaning concrete or rock; pervious, generally low plants, grasses, bushes, and so on; and pervious, meaning exposed soils. Each of these has very different radiative and thermal characteristics. And then the last one is something we call the thermal inertia of the construction materials. So that is the ease with which these materials heat up and cool down, or the ease with which they accept and release heat. And so we can divide that into 2 very simple categories: heavy materials, meaning concrete, steel, and stone, for example, and then lightweight materials. Heavy materials have a very high thermal inertia. That's exactly why we have urban heat island effects in cities, because those heavy materials absorb and retain heat very slowly, and they retain very large amounts of heat through the night. Lightweight materials are more flashy in their thermal response. They heat up quickly and cool off quickly. So these are the 4 basic characteristics of the urban and rural surface. And from that, if we combine all of those characteristics, we can come up with many possibilities for local climate zones. In fact, we could come up with many more than 17, but we felt that 17 was a reasonable number to capture the diversity and the variability in urban environments around the world. Of course, we had to trim off many of the redundant zones, and we had to create a couple of new ones to capture environments such as lightweight, low-rise, or heavy industry. So this is the standard set of 17 local climate zones. One of the criticisms of this zone of the zone system is that these are much too uniform or homogeneous, and that they don't really reflect the reality in cities. And that's a perfectly legitimate observation. However, we have to remember that a classification system is supposed to be generic. It's meant to be a starting point on which we base research projects and research questions and hypotheses for study. So these are intentionally uniform and homogeneous, And if we work together with these classes and we combine them into subclasses, we can create new classes that are slightly more diversified and slightly more mixed than we see here in the 17 standard zones. Okay, I think one of the most important steps in any study that involves local climate zones is to understand the fundamental definition of what it is. Now, I've broken this down into four smaller definitions that are nested within a larger one. And the first deals with the issue of scale. A local climate zone is an area of uniform surface geometry and land cover that spans horizontal distances of hundreds of meters to several kilometers. Okay, this is essentially the definition of what is local scale in the horizontal dimension. So that's very important when we're selecting a training area, for example, in a WUDAPT mapping project, or we're classifying a temperature sensor or a climate station. We need to consider that area that extends several hundred meters at least. Now that's often a difficult step to do, and we'll come back to that in a minute. The second part of the definition deals with the concept of uniformity. Uniformity is measured in the repetition of roughness elements, meaning the trees, the buildings, and the surface cover types, meaning impervious or pervious, that influence air temperature at screen height. Now, uniformity is very sensitive to scale. When we look at a land area at micro scale, we will see a different pattern of uniformity than we see at local scale, or mesoscale, or macro scale. So that's important to stay within the local scale dimensions and look for repeating patterns. In other words, the repetition of buildings of similar height, or the repetition of spaces of similar cover, and so on. The third point, the characteristic form of a local climate zone gives it a unique air temperature regime that differs from other LCZs of similar relief and macroclimate. So here, this is important because LCZs were designed and defined by properties of the surface that influence the air temperature at standard screen height, which is 1 to 2 meters above ground. Okay, it's important to remember that. There are many studies now that are looking at the radiation balance or the energy balance or the surface temperature of cities and using LCZs as a framework. And that's okay, but you have to remember that this was based on air temperature measurements. And it's also important to remember that there are other features of the landscape that influence air temperature than just the buildings and the built form in the city. You also have to think about the relief of the landscape, the larger macro or regional climate, the wetness of the soils, weather conditions, and so on. So this brings up an element of control. Finally, LCZs provide a standardized physical descriptions of cities and ease intercity and interdisciplinary exchange of urban climate data. This is really the purpose of the scheme and really the output of the scheme. We can describe our cities now in a way that's relevant to the local climate of the city, but also in a way that's very simple and easily understood across many disciplines, not just the traditional geography and meteorology and climatology, but in a way that architects and engineers and planners and city managers can understand. We can also compare results from one city to another, so we compare apples to apples and oranges to oranges when we've used a standardized framework. Okay, so that's a basic rundown of what a local climate zone is. Now, all of that information is contained very neatly in what's called the LCZ data sheet. This is essentially the WUDAPT level 0 data. All of that can be extracted from these sheets. Now, there are a number of key features on here. I just want to run through these quickly, but the first one is the definition, and here we talk about the zone form, the zone function, and the zone location, where you might find that. You'll notice at the bottom of that paragraph is a keyword correspondence, and this enables researchers to make a relation between the LCZ scheme as it exists now and with earlier schemes that were used in previous years, and this is namely the urban climate zone scheme that was developed by Professor Oak in Vancouver in 2004. But the earlier scheme to that was one developed by Ellefson in 1990. That is largely one that's based on American cities, and it doesn't have application across international regions. However, for those people that did use older schemes, it is helpful in the transition into the LCZ scheme by having the zone correspondence. Now, these illustrations here are important. The LCZ scheme is designed to be very visual. In other words, it depends on things like photographs and getting out into the field and observing with our own eyes what these zones look like. And so I stress again and again for researchers to take photographs, but also to use photographs to help classify and to recognize climate zones in cities. So you'll see that these cities apply to different parts of the world. They are not just North American photographs. I often hear that the LCZ scheme is only intended for North America, which it is not, and that is expressed here in this small gallery of photos in each of the data sheets. The last section here is probably the most important, but these are the physical properties of the zones. In here we have 10 different properties. Most of them are fairly easy to collect or to measure in the field or through computer techniques. There are a couple that are not easily collected, such as the anthropogenic heat flux, but that's why we put it there. If you can collect 6 or 8 of the others, you can just assume that the remaining categories fall into the range that's provided in this data sheet. Now, the range is given because this is a generic scheme and because there is quite a bit of intra-zone variability that you might find within one neighborhood or one district, and that range of red bars there allows for that variability. It also makes it easier to measure when we're in the field and to put our sites into one of the 17 zones. Okay, once we've done that and we've made a commitment to using the LCZ scheme, there are essentially 3 steps that we might follow to put a site into its appropriate class. Now, we don't have to go out and gather or measure data for all of the 10 surface properties that define a local climate zone, but we might select 4 or 5 or 6 or 7 and attempt to quantify those as best we can, and then use that to base the classification. So on the left, I've indicated that, you can see, and the types of metadata that we might use to help that classification can come from 3 areas. We can use foot surveys or field measurements by getting out into the cities and walking through them, taking a camera, taking a notebook, and driving around or walking around and looking at what we can see. We can also use the LCZ data sheets, as I mentioned, and then what's becoming increasingly popular is the use of satellite photos, remote sensing imagery, and other online platforms that provide all kinds of very valuable digital data to help us classify our sites. All of this helps us or leads us towards what I call a best fit classification. In this case, it's LCZ2 compact mid-rise. But it's important to remember that this is a best fit. The classifications may not be exact, and that's okay. We can always come back to it later and refine our classifications as we move on through different levels of WUDAPT, for example, up to level 1 and level 2. Or as we go back into the field and gather more data, we can help to refine those initial classifications. But whatever we come up with in this stage is an improvement over simply classifying our sites as urban and rural. Now, what I think is one of the most important tools that we can use in the classification process are photographs. And here I've laid out what I think are the 4 cardinal views of photography that are helpful in classifying a site. In the top left, we have a bird's eye view, and this is very helpful when we're looking at how much of the surface is pervious or impervious, how much is paved, how much is sealed, how much of it is occupied by buildings, what is the footprint of the buildings, and the geometric form of the buildings. But that in itself is not good enough. We need to move over to number 2, which is the oblique view. We need to elevate ourselves and look down into the streets, into the canyons, to get a sense of the building heights, the building spacings, to get a sense of the vegetation in the canyons. And this is important, of course, for airflow and for radiation balances and understanding the temperature regime in these local areas. And then once we come right down onto the ground, which is photo number 3, which is what we call the street view or the canyon view, we get a sense of what is the material of the canyon floor. And we can get a sense of the aspect ratio of the street, or in other words, the height to width ratio of the buildings to the street, and just the building heights themselves. And we can look at the objects in the foreground, such as the cars and the people and the buses, and we can come up with a pretty good estimate of how tall the buildings are and how far apart they're spaced. And then the fourth one is maybe not quite as accessible, the hemispheric view. For this, we need a fisheye photo, for example, and we can take a hemispheric photo looking up to the sky, and we can quantify how much of our peripheral vision is obscured by the surrounding buildings, and this is a very important measure or indicator of the radiation and the energy balance inside those streets. Okay, let's move on. I'm going to go through a couple of problems that I think are leading to some confusion with the LCZ scheme, and these have been communicated to me very helpfully at WUDAPT workshops and in the literature and through personal emails and so on. And one of the common problems relates to spatial scale. Now, I've already covered this to some degree, but I'm going to review it again, and that is the important distinction between local and micro. And at local scale, as I mentioned, we're largely concerned with horizontal dimensions of hundreds of meters to several kilometers. And in this category of climate, we find urban units such as urban blocks or land use zones, districts and neighborhoods, and so on. And next to that is what we call a microclimate, and this is at a much smaller scale. We're going down, in some cases, to centimeters, right up to several tens or maybe 100 meters. And of course, this is associated with the microclimate of an individual building or a tree or even a leaf on a tree, a small park or a garden, for example. This is what we consider microclimate. So this is directly important to the process of classifying our sites or selecting appropriate training areas to create a WUDAPT or an LCZ map. And we have to remember to do this at local, not micro scale. Now, my example here is of an official climate observatory in the city of Quito, Ecuador, in South America. This is the central observatory in the heart of the city. And in some ways, this is not a very good climate site because you can see the red dot is the site, but around the site, to a 75-meter radius, is largely grass and trees and green surfaces. And so the tendency is often to classify the site based on what is immediately visible to an observer standing next to that site, or to a computer operator who may be looking at a satellite photo and can see the trees and the vegetation around the site itself. And if we do that, we'll probably classify this site as LCZB, which is scattered trees with an entirely pervious surface cover around that site. However, if we open up our radius to a local scale, we have an entirely different classification. Now it's probably an LCZ2 with compact mid-rise. So you can see the importance of understanding scale here. Now, both of these scales are important. There's no doubt that the temperature sensor at this climate observatory is influenced by micro scale properties, but more dominant is the local scale, and that's because the surrounding area or the surrounding fetch of that site extends out several hundred meters, and so as the air advects or moves and flows across that broader area, it picks up its properties and characteristics and carries them towards the temperature sensor itself. So that's the importance of scale. There is a way to get around that, and this is what I call a recommended practice, and that is to consider the windrows when you classify your site into an LCZ. Now, this applies almost essentially to a field site rather than to a WUDAPT training area, but nevertheless, it's important to think about the wind direction when you classify your site, and that's because the wind, as I said, carries the properties of the surface across and up to your temperature sensor. And so that's what we mean when we say a thermal source area, or a footprint area, or a circle of influence, or an area of influence. And that we can see here in the pink area, okay? And that's based on the windrows here, which tells us the frequency and the direction of winds that are measured at a particular point. And here it's suggesting that the winds are most frequently coming from the southeast, and so we may take into consideration the southeast quadrant next to our site here. And so that will have a better influence or a greater influence on how we classify that site. And so here we are probably inclined to put it into an LCZ6 rather than an LCZ8 over here, because the winds coming from this direction are less frequent. Now, stemming from that is a general principle that we should avoid LCZ borders or overlapping zones or unclassified areas when we're measuring our temperatures in the field. And that's precisely for the reason that there is a advection of air across surfaces that have very different form and cover, and therefore have different thermal properties. So when we run our survey routes through the city here, select points that are away from transition and LCZ border areas, or even areas that cannot be classified into an LCZ. And so you can see that that's what I've illustrated here. Each of the points is in the center of the polygon, the LCZ polygon, and this will give us reliable and representative air temperature measurements of the surrounding urban form. Okay, the second one is what I call confusion of surface geometries. This is very simple, but interestingly, it's one that's quite often confused, and this has been expressed in the literature, but I've also seen evidence of it at previous WUDAPT workshops, and that is the simple distinction between a high-rise, mid-rise, and a low-rise zone. And I've illustrated here, you can see that the distinction is entirely based on the number of stories and the height estimate of those buildings. So high-rise meaning many tens of stories and generally greater than 25 meters, and so on for mid-rise and low-rise. Now, the problem I think arises from from reliance on two-dimensional satellite imagery, and here's an example from the center of Mexico City. This is one of the largest cities in the world. The core area is very compact, as you can see here, but it's not easy to get an impression of how tall those buildings are and what is the variability of those building heights. And so for that, my recommendation and my favorite way of studying LCZs is to get into the field, is to get into those streets and to walk through them, or ride your bicycle or drive a car, and to observe and to take photographs and to gather as much field data as you can. And so you might do a reconnaissance survey through these street canyons here, and as you go through, you can easily guesstimate the heights of the buildings if they're low-rise, mid-rise, or high-rise. That is a very simple exercise, simply by counting the number of floors. And as you're doing that, of course, you're collecting important site metadata. Here I'm showing a photograph from the street level of an intersection, or a fisheye photo of the sky, or getting up to a high point, maybe an observatory on the top of a building, or going up to the top floor of a building, or to a hilltop, and taking photographs down at an oblique angle into the city streets. And all of this is very helpful to get accurate estimates of the average building heights inside of a local climate zone. Okay, now if all of these good practices are followed and recommended practices are followed, this of course inevitably produces good outcomes. And I'm going to go through a few of these from the international literature now in three areas: measurement, modeling, and mapping. And all of these have become quite common now. There are emerging literatures or sub-literatures on each of these fields. Measurement, of course, is being the most popular, but the mapping and modeling are certainly surging ahead as well. And I'll start with what I think is maybe an example that is most faithful to the original aim of the LCZ scheme, and that is mobile surveys, vehicle surveys through the streets of Vancouver. And these are data that come from Professor Tim Oak, who is, of course, the co-author on the local climate zone. And he, of course, taught for many years a course on urban climatology. And in 1999, he sent his students out through the streets, collecting all kinds of temperature data. Now, I was able to go back and to retrieve those data. So this is a good example of how we can reclassify historical data sets, if we have the site metadata, into local climate zones, and now we can do valid comparisons with studies of today. But these data are excellent. You can see as the traverse passes through the city and in and out of different LCZs, the temperature is quite different. And what's quite striking on this is that within each of these LCZs, we can see that there's spikiness or intrazone variability in temperature. In some cases, it's more than 1 or 2 degrees, and that's perfectly normal. That happens as we pass through different intersections, or under a bridge, or over a bridge, or under a tunnel, or through a shady part of the street, or we're idling next to a truck that's emitting a lot of heat, and so on. So we would expect these micro scale temperature variations. We're more interested in the local scale, so we might average those variations out across the scale of a local zone. What's also important here is across the bottom. I've shown that the elevation is quite variable. Vancouver is a mountain valley city, and so we have quite a range of elevations and relief characteristics within the landscape, and these, of course, are part of a strong influence on the temperature observations in the city. So we have to remember that. And so we try to collect our data not only when it's clear and calm weather, but also when the soils are dry. And this promotes the formation of local climates, and it gives us some control over the environmental conditions. And of course, when we're looking at these data, we also have to remember that elevation and relief also influence the local climate temperatures. Okay, here's a nice study in Berlin, which was published just last year. This was a study that relied on several hundred citizen weather stations across the city that were in operation for a year, and the authors classified all of the citizen weather stations into LCZ classes, and they came up with this very nice pattern. It essentially confirms what was shown in the previous slide, and that is that the local climate zones that have more green surface cover and more trees tend to be cooler than those that have, of course, building features. And those zones that are most compact, with the heaviest construction materials, tend to be the warmest when we're doing nighttime observations of the air temperature. And these patterns are being repeated over and over in different cities around the world, so it's giving some confirmation that the LCZ scheme is a fairly robust system with which we can classify our cities. Interesting here is that the differences between the temperature are greatest in the summer, and they decrease in the winter, and that is largely a response to the weather conditions. Berlin is quite hot and dry and sunny in the summer, and so those conditions promote LCZ temperature differences. And the winter it's cloudy, and so temperature differences are subdued. Okay, this is one of my favorite tables. This comes from a study that was published last year in the International Journal of Climatology. This is the city of Szeged, Hungary. It's a small city in Central Europe, and in that study, the investigators installed a network of about 20 climate stations across the city. They classified those stations into their appropriate LCZ classes, and they collected continuous temperature data for 12 months. And rather than just producing a study of the urban heat island, which we don't really need any more of in this city, they produced a table of temperature indicators that are useful and applicable to many disciplines and to many professions, such as agriculture and energy and water use, and so on. These indicators are important to city managers in particular, but also to planners and engineers and so on. And when we present numbers like this, they certainly sit up and take notice. Now take a look. If we look at the cooling degree days, for example, this is a measure of the energy demand, building energy demand for building cooling. And you can see that there's a significant difference between the four LCZ classes. LCZ2 has the highest cooling demand, suggesting that the air temperature in that zone is the highest. And it's about 30 or 40% higher than LCZ9 because it's a much cooler zone. Frost days are important for agriculture. We can see that there are 51 frost days in LCZ9, but if we move into an LCZ2, we have significantly fewer frost days. Tropical nights, we have a big difference again. The last category is fun. This comes from a German concept of beer garden days, and that is measured based on the temperature at 9 o'clock at night. If it's greater than 20 degrees, this, of course, is meant to encourage people to come out of their houses and into the streets and go have a drink in a beer garden. And so The data there suggests that there are 81 beer garden days in LCZ2, but only 45 in LCZ9. So these data are very interesting. They tell us something about not only the environment of the city, but also about the culture of the city, the lifestyle of the city, the recreation of the city, the efficiency and the sustainability of the city, and so on. And so that is taking the LCZ scheme beyond just an urban heat island tool, but also something that's useful across many disciplines. Okay, let's look at some modeling studies. This is ENVIMET. These are simulations that were run in the city of Phoenix, Arizona in the United States. It's a hot, arid desert city. ENVIMET is a three-dimensional microscale model, and these investigators looked at different LCZ configurations or urban configurations and put them into the model, and they modified the surface cover depending on different landscaping types. You can see that on the left is mesic and on the right is xeric. Xeric is a type of landscaping that uses native plants, native desert plants that do not require much water and very little, if any, irrigation. Mesic is the opposite. It uses plants that are not native. It requires a significant amount of water to sustain those plants. So these are very different landscaping types and also different building configurations. And so they ran the models for many different simulations, mostly for afternoon air temperature, because Phoenix is a very hot city, and the investigators want to know what building configurations or what LCZ configurations are more conducive to afternoon cooling, along with different water regimes and, of course, different landscaping approaches. But you can see that there's a big difference between the different classes and the different landscapes. They did come to a conclusion that compact urban forms led to more cooling than open forms, and of course a mesic approach did also lead to more cooling, but of course is much less sustainable due to water consumption. But these are some of the questions that can be addressed and that can be answered with an LCZ framework. Now, this will be familiar to many of the people. This is a WUDAPT map of Kolkata, India, following, of course, all of the WUDAPT methodologies that have been developed, and this is created through automated techniques. This is a very impressive map. You can see how complex the urban form of Kolkata is. You can see how the different zones sprawl out from the old core into the countryside. You can get a sense of how much land has been converted from rural to urban, and in particular, what kind of urban, whether it's a compact or lightweight or open or treed and so on. So what I think is most valuable about these WUDAPT maps is they give us a wealth of spatial statistics that tell us something about the morphology of these cities, about the suburban sprawl, land cover change. And then these are cities that we almost know nothing about in terms of these things. And so this data can be collected fairly easily for any number of cities around the world. And that, of course, is the benefit of the WUDAPT methodology. Now, one word of caution is that it's a little difficult to make inferences about the local climate inside of these maps because they are pixel based, and you can see the image takes on a very speckled or scattered look because I think it's done at a 100 or 200 meter resolution, and of course local climates do not follow pixels and they do not follow grids, and so we have to be careful when we look at a map like this if we want to make some inferences about the local climate inside this area. If we do want to do that, we should probably better following a manual mapping approach, and this is one that was done very effectively in the city of Ouagadougou, which is in Burkina Faso in West Africa. Now, these researchers took an entirely different approach. They gathered all kinds of metadata through maps and satellite images and so on, but they did not do an automated pixel-based classification. They actually mapped it out by hand using the metadata that was gathered not only in the field but also through computer programs. Now, they were able to divide the city up into about 4 or 5 different classes, and they used that to develop a spatial framework within which to place their temperature sensors. And so this was to underlie a basic climate study in this city, and they were particularly interested in investigating the influence of urban morphology and vegetation on nighttime cooling rates of air temperature in the city. And so they use the LCZ scheme to guide them in the placement of their temperature sensors around the city. A very, very interesting study and very well done. Okay, I'm going to finish now with what I call the golden rules of success with local climate zones. These are rules that I've come to over the years of working with people and collaborating with different projects, such as the ones I've shown on the previous slides. And what I found is that there are three things to keep in mind. One is that we always have to anticipate challenges and uncertainties with LCZs, and that is partly because no classification system is perfect. So if we put our site or our subject into its appropriate class, it's quite possible that we have to go back and revise that class, or it's quite possible that there are errors in that classification process. And this is entirely normal. It is an inherent feature of every classification system. They are meant to be generic, and when we put something so generic into a complex urban environment, we're going to face challenges. So expect that. Number two, always remember the original aims and assumptions of the LCZs and adjust your expectations accordingly. So as I said at the very beginning of this presentation, the original aim of the LCZ scheme is to bring a more nuanced description of cities that is relevant to local climate and in particular to air temperature. Okay, there are lots of studies now on surface temperature, on energy balance of LCZs, and sometimes those don't always work out the way the investigators hoped, and that's largely because they're taking the original scheme and using it in a derivative purpose, and so the expectations may not be met. So it's important to remember that. Number three deals with something we call experimental control when we're studying the climate of a city, and that is to recognize that surface relief, soils, vegetation, slope aspect, and built form all can influence the local climate of cities. Now, the LCZ scheme largely deals with, of course, soils and vegetation and buildings, but it does not deal with relief and slope aspect. Okay, so if you're comparing temperatures within cities or between cities, those differences can be explained in part by the LCZ scheme, but you also have to think about other things like relief and the larger regional climate within which your city rests. Okay, I'm going to end with that, and I'll just say again that I really look forward to hearing about some of the outcomes from this workshop on WUDAPT and LCZ, and I think it's very encouraging that the Chinese cities are adopting or entertaining the idea of using LCZs. I hope that it's helpful. I think there is a great potential for Chinese cities to adopt the LCZ scheme, and I think that the material that is going to be presented in the next couple of days in this workshop will be just wonderful, and I'm sure it'll help to in the exchange of very important information on cities and their environments and their sustainabilities and so on. So with that, I'll sign off. My very best wishes to a successful workshop. Thank you.